Hello, we're in section 5.3. This is page 239 and still looking at conditional probability. So this is question number 30. You're tossing two fair dice. One is dark green and one is light green. That drives me crazy. I wish one of these dice could be red, but it's not. I didn't make the rules. So the event Y is that you roll a sum equal to 6 on both of the die, and event Z is defined as rolling doubles. The question asks, are Y and Z independent events or dependent events? And you must show your work. So on a test, you are not allowed to say, no, they are not independent, or yes, they are. You have to show your work. How are you going to do this? Well, you're going to calculate the probability of Y, and then you're going to calculate the probability of Y given Z, and if they are the same, that is, if probability of Y given Z equals probability of Y, then yes, they are independent. You could also do, if probability of Z given Y, Y, you could also say if that equals the probability of Z. You could do it either way. I just picked Y somewhat arbitrarily. So to answer these and find these probabilities, we look at this table. The book has a figure you're welcome to look at, but if you want help finding the sums, you can do it in a table like this. So here's the dark green die, here's the light green die, and this table on the inside represents the sums. So 1 and 1 is 2. I got a 2 and a 1. I'm rolling 3 there for the sum. You can see this kind of has a pattern here, 4, 5, 6. And then I got a 6 and a 1, that's 7. I'm going to pause it while I fill in the rest of these sums. I'm back. So I filled out the sums, and I'm going to use this to answer the questions about probability. So I'm going to go to this chart here. Let's make it black, and let me give myself a white pen. So I want to find the probability of Y, and in this case, again, Y equals roll a 6, and Z equals doubles. So the probability of Y equals the probability that you roll a 6. So if you look at this table here, 6s are right here. 1, 2, 3, 4, 5. There's 5 ways to roll a 6 out of the 36 possible sums that you could come up with. So the probability of Y is 5 of the ways divided by 36 total sums that you could come up with. So the probability of Y given Z, here's the formula. That's the probability of Y and Z, all divided by the probability of Z. So we're going to do each one of these separately. What's the probability of Y and Z? That's rolling a 6 and getting doubles. Again, look at our little table. Rolling a 6 and doubles. Well, there's only one way to do that. It's right there, as you can imagine. You have to get 2 3s in order to get a 6 and doubles. So there's only one way out of the 36 that you can get a 6 and doubles, and the probability of getting doubles, which is the probability of Z, again, you can see this pretty quickly. These are doubles right there, all these on the diagonal this direction. 2 1s, 2 2s, 2 3s, etc. So there's 6 different ways you can roll doubles. Again, I think most of you would have seen that right away. So there's 6 different ways you can get doubles out of 36 possible ways. You can roll sums. So the 36's cancel and we get 1 out of 6. So now we see that the probability of Y is 5 out of 36. The probability of Y given Z is 1 out of 6. So these are not the same. Probability of Y is not equal to the probability of Y given Z, which is 1/6. So because they are not the same, we're saying knowing that Z, if we know Z, that changes the probability of Y. So these events are, you could either say not independent, or you could say they are dependent or they are conditional. I'm happy with any of those wordings. So that's how you work that problem. A lot of little tedious math.